this class. Sampling theorem will be continued. Yeah, so let's see what we did in the last class quickly. Yeah. So what we did was we have taken a continuous time signal. So yeah, so I have understood. So we have taken a continuous time signal x of t. So x of t, a continuous time signal, and a continuous time signal with band limited meaning its frequency content is band limited to omega m. Omega m is the frequency in radians, right? It's not the hertz, it's the frequency in radians per seconds, or it's called radian frequency. That and x of j omega is what we considered it's band limited. So x of j omega is 0. Say this is omega m, this minus omega m. So this is x of j. So x of j omega is 0 for omega greater than or equal to omega m. That meaning for minus omega m, yeah. So anyway, so we have taken that signal and we tried to sample this signal. So this is the frequency domain description of the signal, and then we tried to sample that using P of t. P of t is nothing but a periodic impulse signal. P of t minus anti this n is equal to minus infinity to plus infinity. So it's a periodic impulse. And this is 0, t, 2t, minus t, and so on. So what we do is this is equivalent to sampling the signal at every t units. So as it corresponds to every t units, we can represent as sampling ts. We can put it as ts. So S stands for sampling, right? We have changed T to TS. In the last class, we discussed this period to be T, and in this class, we just changed the symbol. We just changed the notation. So instead of T, I am writing it as TS. TS stands for sampling. And then we multiplied this x of t. This x of t signal, we are multiplying with P of t. Right, and then what we are getting is xp of t. So this is all we did in the last class. So xp of t is nothing but x of t multiplied with p of t. So that meaning this is x of t. What is p of t? Delta of t minus nts. N is equal to minus infinity to plus infinity. Right, this is all we did in the last class. Here I have the period equal to t. Now I am saying the period, I just changed the notation to ts, just to emphasize the fact that we are sampling at every ts. We are getting one sample every ts seconds, right? So when I multiply x of t with p of t, what do I get? So let's assume our x of t is something like this. Say let's say this is our x of t. X of t, and then this is my p of t. P of t is a set of impulses, right? This is 0, ts, 2 ts, minus ts, minus 2 ts. So when I multiply these two, what will I get? I get a set of impulses. So let me I'll get my sample here will be of this height. This will be slightly higher, and this will be a lower sample, and this will again be a larger sample. This will be a lower sample. So this is 2 ts, this is ts, this is 0. So this signal we are calling it as xp of t. So this is time axis, this is time axis, right? So when I multiply this signal, when I multiply these two signals, I'm getting this signal, right? So and that meaning I am sampling this signal at regular intervals of ts. You understand? So there is a continuous time signal. We are observing that signal only at 2 ts, 0, again another at another ts, another ts. So xp of t is the sampled version of x of t, and sampled at and it is one sample taken every ts seconds. One sample taken every ts seconds, right? In ts seconds, one sample, then next sample comes at another ts, and so on. And then we wanted to, so in the last class we started analyzing this situation in the frequency domain. We started analyzing in frequency domain. So so in frequency domain, that meaning in Fourier transform domain, xp of j omega is x of j omega convolved with p of j omega. Its Fourier transform is x of j omega, its Fourier transform is p of j omega, and its Fourier transform is xp of j omega. What is that? So this is all in the time domain, left hand side. This is all in your in time domain, and in frequency domain, what do I have? So this is x of j omega. X of j omega, what did I say was, this is a band limited signal. So this is limited to omega m to minus omega m, and this is an omega scale, and so this is x of j omega. So this is its Fourier transform, right? And then what is the Fourier transform of p of j omega? It's a periodic impulse train. So let me write this as this is omega s, this is 2 omega s, this is minus omega s, and then minus 2 omega s, and so on. So it goes on forever, right? Here, what is omega s? Omega s is equal to 2 pi by ts. Because p of t is periodic with period ts, its Fourier transform will be, so p of t is a periodic impulse train. This amplitude is 1. P of t is periodic impulse train with period ts. Then p of j omega, its Fourier transform is also periodic impulse train with period omega s, where omega s is equal to 2 pi by ts, and its amplitude is 2 pi by ts. The amplitude of each of these things is, right? So now we have to convolve these two signals. Okay. So when you convolve these two, what do you get? So we have to take this convolution. If you do this convolution, you will get xp of j omega. So let me write this a bit below so that you won't get confused. So this is omega axis, and what I'm trying to say is omega s is equal to 2 pi by ts. So if I convolve these two signals, I'll get xp of j omega, and that's where we stopped in the last class. So in the last class, I tried to show you that convolution of these two signals, right? Convolution of these two signals will become something like this. Yeah. Okay. So maybe the diagram I will write like here. So here. So I'll. Say 0. So this xp of j omega, and this is ws, and this is 2ws, and this is minus ws, and minus 2ws, and its amplitude will be 1 by t. So please note down these amplitudes. This is 1, this is 2 pi by ts, here its amplitude is 1 by ts, right? So in the last class we did till this. So this is the convolution of x of j omega into x of j omega and p of j omega. Okay, so let me write this down more mathematically, right? So I'm just sorry. I'm just trying to squeeze everything in one page. Why? Because you can have everything together. Xp of j omega is convolution of x of j omega with p of j omega. So this is nothing but this is x of j omega convolution with what is p of j omega? 2 pi by ts delta of omega minus k omega s, k equal to minus infinity to plus infinity. That becomes, so this is still the convolution. That becomes 1 by ts so x of, this is x of j omega into delta of omega minus k omega s. Let me check this down. Yeah, this is not into, sorry, there was a mistake here. So this is x of j omega minus k omega s. Yes. Yeah. So just take another 2 minutes. So first, if you multiply x of t with p of t, you get xp of t. This is the time domain description. So to get frequency domain description, we have to take x of j omega. So we have taken x of j omega. X of j omega, we assumed that as a band limited signal, band limited from minus omega m to plus omega m. And here I just assumed that x of j omega's Fourier transform is triangular in shape. It can be any shape. This is just an example we are taking. Right? X of j omega can be of any shape, but the important point is x of j omega is non-zero only over a finite interval. Like x of j omega is non-zero only over this band minus omega m to plus omega m, and it is zero everywhere else. So that's why it is called frequency limited or band limited. Band limited meaning in the frequency band it is limited to only certain portion of the frequency, and it is zero at other frequencies, right? So this is x of j omega. Then p of t is a periodic impulse train. So its Fourier transform is also a periodic impulse train with amplitude 2 pi by ts, and its repetition is at regular intervals omega s. So now we have to convolve this x of j omega with p of j omega, and whenever and the convolution is the result will be this x of j omega is repeated at each impulse of p of j omega. See, when you do convolution of any signal with an impulse with delta of t or with a unit impulse, then the same signal will reappear at the location of the same signal will reappear at the location of the impulse. So that's what I'm trying to say is that so this is just to help you remember things. Convolution of any signal with this is I have given you as an exercise with unit impulse will result in the same signal at the location of the impulse. meaning, say in frequency domain, I have a signal. Say this is just some an example. So x1 of j omega to omega, and this I want to convolve with delta of omega minus some omega naught. So what is delta of omega minus omega naught? That means at omega naught I have an impulse, right? So this is delta of omega minus omega naught. If I convolve these two signals, so if I convolve this with omega naught, so convolution of these two will result in, see, the same signal reappearing at omega naught. So this is omega naught, and hence centered at omega naught, this same signal will reappear, right? So this is x1 of j omega convolved with delta of omega minus omega naught will be the signal. So whenever you have impulses, your convolution integral will be very easy. The original signal this signal will reappear at the location of this impulse. See, that's what exactly we did here. So by following this property, when we convolve this x of j omega with p of j omega, see, this is the original signal. This reappears at the location of 0, at the location of omega s, at the location of 2 omega s. That's what exactly we did, right? So the same triangle will reappear at the location of 0. The same triangle will reappear at the location of omega s. The same triangle will reappear at the location of 2 omega s. Right? And then you have to take care of these things. What are this? So this is omega m. This is minus omega m. Because this triangle is of width, it is from minus omega m to plus omega m. So this will also be of width omega m, but this point will be omega s minus omega m, and this point will be omega s plus omega m, right? Because from omega s it will be minus omega m, it will be plus omega m. Similarly here, this point will be minus omega s plus omega m, and this point here will be minus omega s minus omega m, right? Okay, so now we have the convolved signal, and this convolved signal, this work I have given you as an homework, like show that the convolution of x of j omega with p of j omega is something like this. And one very important assumption that we made in computing xp of j omega is, we have assumed that omega s omega m is greater than, so hope all of you have noted this down, right? So I'm sorry, this page has become very dense, like there are so many diagrams and so much writing, but anyway, I'll mail you this as a PDF again. So last time I hope all of you have received that file, my class notes file, which I mailed as a PDF. It's a huge file though, it is a 25 MB file, but again that will help you even if you miss some of the notes. Okay, so see, if you carefully observe this diagram, here what's happening is, we have assumed that this omega m is less than omega s minus omega m, right? We have assumed that so let me write that with say different. Omega m is less than omega s minus omega m. Just see these 2 points, right? So you please observe this. Even if you don't note down in your notes, that's fine. But you try to understand this first. Anyway, I will mail you the notes. Okay. Yep. So this is about convolution of the signals. So one important point is in determining xp of j omega, we have assumed that omega s we did this assumption, omega m is greater than omega s minus omega m, which implies that, sorry, this should be the other way. This should be omega m is less than, is that what we did here? Yes. So this implies that omega m is less than 2 omega s. So we are assuming this and we are going forward. Assuming this, we derived xp of j omega. Now, right? So this we are close to defining sampling theorem. So now, okay, we have taken, let's again go back to this diagram. We have taken x of t, we sampled at ts seconds, we obtained one sample every ts seconds, we got xp of t. Then we observed in the frequency domain that the Fourier transform of xp of j omega, the Fourier transform of xp of t, which is xp of j omega, has got the same spectrum x of j omega repeated at every omega s. Now we want to get back the original signal x of t. See, just think how we started all our discussion. How we started the sampling discussion was, we said if there is a continuous time signal x of t, which is frequency limited to some frequency omega m, right? If there is a continuous time signal x of t which is band limited or frequency limited to some frequency omega m, then we can sample the signal at some rate. We can sample the signal, and then from those samples we can get back the original signal x of t. We said that by sampling the signal, that the samples uniquely represent x of t. What does that mean? When I say the samples xp of t, the samples xp of t uniquely represent x of t, that means I should be able to get back my x of t from xp of t, right? See, when I sample, and after sampling, if you give me the samples, I should be able to get back to the original signal. Otherwise, I cannot claim anything. Otherwise, it's simply useless, right? So now we have to see that, can we get back to the original signal x of t from xp of t? Can we do that? Yes, we can do that from the frequency domain interpretation. So now we have the signal xp of t, whose Fourier transform is xp of j omega, which is shown here. So in this Fourier transform, if we extract only this portion of the signal, right? So if you just focus on this thing, if we extract the center portion, which is from minus omega m to plus omega m, that means we are done. Say for example, now if I put a low pass filter, if I put a filter and extract this portion of the signal, right? Then that means I got back the original x of j omega, right? So that means from the sampled signal, if I get back the original Fourier transform, if I get back this x of j omega, then I will take an inverse Fourier transform and I will get back to x of t. That's it. Understood? So let me write this down, and then again we'll come back here and then we'll discuss. Okay. So observe that xp of j omega, what xp of j omega contains x of j omega repeated at every omega s. If we extract x of j omega from xp of j omega, through a, okay, I'll write this in full. It means that we can reconstruct x of t from xp of t. So what do we do? Use a low pass filter So this low pass filter, we will call it as LPF. Use a low pass filter that extracts x of j omega from xp of j omega. So right. So what I'll again draw the diagram here otherwise. So we have, this is our xp of j omega. We have xp of j omega. Its amplitude is 1 by Ts. This minus omega m, this omega m, and this is, sorry, this is plus omega s, and this is 2 omega s, and so on and so forth, right? So this is minus omega s and so on. So what I'm trying to say is, we know that our x of j omega is having an amplitude of 1 here, and it's exactly equivalent to this triangle. So what I'm trying to say is that you put a filter here, a low pass filter. What we want to extract out is this portion. So simply put a filter here. So this filter should be, what should be that filter? So that filter should have an amplitude of, and what we need is omega m should be less than or equal to omega c should be less than or equal to omega s minus omega. So if we use this filter, then we will get back our x of j omega, right? That meaning we are able to successfully reconstruct the original signal x of t from sampled signal xp of t, right? Yeah. So now let us put everything together, right? So if we put everything together, what we will get is something like this. So you have continuous time signal x of t, which is band limited in frequency to omega m, and then that we are multiplying with p of t, periodic impulse train, with period equal to ts, and then what we got was xp of t, and then this we are giving it to a filter. Yeah. So here that's correct. So here what I'm saying is that, and omega s is greater than or equal to 2 omega m, then here what is xp of t? Sampled version of x of t, then h of j omega is a low pass filter, an LPF having this characteristic. It's an ideal LPF having cutoff frequency. Okay, so hope all of you know about filters, like low pass filter. Low pass filter is the one which passes frequencies around 0. So it passes only the low pass filter, sorry, low frequencies. So low pass filter passes the frequencies around 0, that means which are low frequencies. A high pass filter passes frequencies of high value, in the sense at those frequencies which are farther away from the 0 hertz, right? So you have these filters and all coming up in your next unit, linear time invariant systems. So as I was saying, ideally the sampling chapter should be after your linear time invariant systems, which is your unit number 4. Because in unit number 4, LTI systems, you will study convolution in depth, you will study filters, and these two things are required for you to understand sampling. So the sampling comes before LTI in your syllabus. So let's live with it. That's it. So h of j omega, this is h of j omega, and its amplitude should be equivalent to ts. Then xr of t is equivalent to x of t. So this is what we did till now. This we will write it as a theorem. So the theorem says that if x of t is a continuous time signal band limited to omega m, and if we sample this signal at a rate with sampling frequency omega s, which is greater than or equal to 2 omega m, then from that sampled signal xp of t, we can recover the original signal x of t by filtering the sampled signal with a low pass filter having its cutoff frequency. So here another condition is this omega c should be less than or equal to omega s minus omega m, and it should be greater than omega m. Right? Then we can reconstruct the original signal x of t. So this is what sampling theorem says. Now we can state sampling theorem. So this is actually equivalent to the sampling theorem stated in a diagrammatic form and with these points. But let's write this as one continuous paragraph, which is required for your exams, right? So I'll quickly write this. Let x of t, you can find this definition from the textbook which I am following, that Oppenheim and Welsky. But anyway, for your notes purpose, I am writing it. Let x of t be a band limited signal with its Fourier transform x of j omega is equal to 0 for omega. Then x of t is uniquely determined by x of t is uniquely determined by its samples x of nt taken. Okay, so let's call this x of nts taken at n is equal to 0 plus or minus 1 plus or minus 2 plus or minus 3 and so on, if omega s is greater than 2 omega m. So where is this omega s coming from suddenly? So this omega s is nothing but 2 pi by ts. Or equivalently, if your ts is greater than pi by omega. Now so whatever I am writing here is whatever we discussed in the previous page, whatever we discussed on the previous page with this diagram and everything. So see, whatever we discussed here, I'm just writing these things in words. So here we says that if we sample at frequency omega s, or if we take one sample every ts seconds, where ts satisfies this criteria or omega s satisfies this criteria, then those samples uniquely represent the original signal x of t. Now if we are given these samples, how do you reconstruct? So the first part of the theorem or the main part of the theorem says that if you have a continuous time signal x of t band limited to omega m, then you can uniquely represent that signal as a sampled signal if you take the samples at a sampling frequency omega s, which is greater than or equal to 2 omega m, or with a sampling rate ts, which is greater than or equal to pi by omega m. But now, given these samples, how do you reconstruct the original signal? So that we are stating it now. Given these samples, x of and ts, we can reconstruct original signal x of t by generating periodic impulse train in which successive impulses have amplitudes that are successive sample values So I'll tell you what this is in a minute. You can just note down successive sample values x of t and ts and period equal to ts. So this impulse train is then passed through a low pass filter. So what I'm trying to describe here is this portion, this last portion of the diagram. So we described up to this portion. Now we are trying to describe the last portion in words. This impulse train is then passed through an ideal LPF with gain T. Is passed through an ideal LPF with gain TS and cutoff frequency omega c, where omega c satisfies this constraint omega s minus omega m. The resulting output signal, if we did so, right? If we did so, the resulting output signal will be exactly equivalent to x of t, right? So the resulting output signal of LPF will be x of t. So you can just note down this, and then I'll just take 2 minutes break, right? And then I'll come back, and then we'll discuss this further. Yes. we just now will discuss what is Nyquist rate. There are some definitions and all. Okay, so you keep working on it. I'll just mute my voice and video. So let's get back to the class, right? So now let's quickly coin some of the terms. So this sampling frequency omega s, if it is equal to 2 omega m, this is called the Nyquist sampling frequency, and this is the Nyquist sampling rate. And let me write that down. So that, yeah. Okay, so I want to clarify a couple of things. See, this see when we say omega s or omega m or express, they're called the radian frequency, or their units are radians per second, right? But you know this relation, omega is equal to 2 pi f. So this is in radians per second. This is cycles per second, right? If you express a phasor, if you express an exponential signal as a phasor, it is angular frequency, and this is how many rotations per second. So that meaning omega s, I can write that as 2 pi fs, where fs I can express in hertz or cycles per second. Similarly, omega m, it is nothing but 2 pi fm, where fm is hertz or cycles per second. So why I am writing this is, in your exam, maybe the frequency can be mentioned in hertz, which is cycles per second, right? Or maybe it is mentioned in angular frequencies, in radian frequencies, which is some 0.4 radians per second and so on. So you should remember these conversion factors. This you know from your very first basic electrical engineering courses, right? So that yeah. So if you state this in terms, when I say omega s should be greater than or equal to 2 omega m, this is equivalent to 2 pi fs should be greater than or equal to 2 into 2 pi fm. So if I cancel this 2 pi, this implies your fs is greater than or equal to 2 fm. So what is fm? Highest frequency component. Highest frequency component in your continuous time signal x of t, and this is the sampling frequency. Sampling frequency in hertz. Right? Say if you are asked that there is a continuous stream signal which has got a highest frequency of 100 hertz, what should be its minimum sampling frequency? So the minimum sampling frequency should be 2 into 100 hertz, that should be equivalent to 200 hertz. Or if you are asked that I have a frequency, I have a continuous time signal x of t whose maximum frequency component is 0.5 radians, what should be its minimum sampling frequency? So it should be 0.5 into 2, which is equivalent to 1 radian per second, right? So just remember this conversion and don't get confused that okay, we studied all this sampling theorem in terms of omegas, in terms of radians, but here the questions are in terms of hertz or cycles per second. Then how to do it? You just use this conversion formula, and all the results we derived so far will be applicable even when you use this conversion formula between Fs and omega s and Fm and right. So from this discussion so far, what we understood that the sampling frequency should be greater than or equal to 2fm, or equivalently it should be something like this, right? So that meaning the minimum sampling frequency is equivalent to twice the maximum frequency component in the signal to be sampled, twice the maximum frequency component, which is equal to omega n. So the minimum sampling frequency is called Nyquist frequency. The minimum sampling rate omega s or equivalently Fs is called the Nyquist rate. Why? Nyquist is a scientist at Bell Labs in the United States of America. So there used to be this Bell telephone systems. So Bell Labs. So there in 1920s he wrote a paper on sampling theorem. So and he derived this lower limit, and that's why it's named after Nyquist. So it's called Nyquist rate. So Nyquist rate is also equivalent to Nyquist frequency. So Nyquist rate, Nyquist frequency, Nyquist sampling frequency, all these are same things. And this interval, the sampling interval Ts, so the sampling interval Ts should be greater than or equal to pi by omega m, right? So when Ts is equal to pi by omega m, it is called the Nyquist interval. The minimum sampling rate or maximum sampling interval. Nyquist interval, sorry. Or in other words, see here it is the minimum sampling rate is called the Nyquist sampling rate. Here the maximum sampling interval is called the Nyquist interval. So this is important and this is important. Yeah, so this is all for the sampling theorem. But now we have to see, so whatever we discussed is ideal sampling theorem, right? Okay, then we'll go back to the practical aspects of it. We'll go back to the practical aspects of it. Note that the LPF, note that the low pass filter, one more point is LPF we considered is called the ideal LPF. It is the ideal low pass filter. Why? Because see, a low pass filter, it needs some rise time and some fall time generally. So if you read circuits, if you do some courses on electronic circuits and so you will understand that no circuit can instantaneously have a response. Like in the frequency domain, what we considered was this response, right? This response, but this is called an ideal filter, because in practice you cannot have a filter having the sharp cutoff. So you can only have a filter having its response increase gradually and decrease gradually. So anyway, you study these more of these things in your other courses, and also when we studied the next unit on LTI systems. So you just keep in mind that whenever any question says it is there is something called ideal low pass filter, it is nothing but whatever low pass filter we considered is nothing but the ideal low pass filter. Yeah. Now let us quickly talk about some of the practical aspects. So what are the practical aspects of sampling? See, when we first discussed the sampling, we assumed that x of t is given a continuous time signal x of t. We want to sample that, and then for the sampling purpose, we assumed we have p of t. We have p of t. P of t is nothing but a periodic impulse train. Recall that we sampled x of t by multiplying it with p of t, where p of t is a periodic impulse train. Right? So you must be noticing that an impulse raises all of a sudden. So what is an impulse? An impulse at time t equal to 0 is, it is 0 till this moment, and it rises all of a sudden, right? So Such impulses are practically impossible to realize. You cannot generate impulses. You cannot generate a true unit step. You cannot generate a true unit impulse, because every circuit, as I just said, every circuit will require some finite rise time and finite fall time. Like if I want to generate, I can at most generate a pulse something like this. So I can at most generate a pulse something like this, or I can narrow it down, right? So these impulses are practically infeasible, practically impossible to use. So we use it that only for our mathematical analysis to understand the sampling theorem, right? It is practically impossible to generate and or transmit unit impulses. What do I mean by that? Delta T's, right? So in practice, okay, we use very narrow pulses in place of impulses. So as I just said, see, in I need to have an impulse. Instead of impulse, I might be having a very short pulse, which is increasing like this and decreasing like this. Right? Say this is 0, this is TS, this is 2TS, and so on. Right? So these impulses will or to be, it's more easy for us to analyze if we consider them that they are short pulses. They are short pulses of finite duration. Sorry. Right? So what we consider in practice is we consider pulses something like this: a short pulse, a narrow pulse. Say this is from minus TS by 2 to say minus T1 to plus T1. And then, so this is at 0, so this is at TS. So this is 2TS, and this we use this as our P of T. As we cannot, so the whole point is, as it is practically impossible to generate an impulse having 0 duration. An impulse has 0 duration in the time domain, right? It all of a sudden it rises and then it decays at the same moment. It is impossible to have impulses. We use a very narrow pulses, a highly narrow pulses, something like this, and use them as the impulses and use them for sampling. So this when you sample your signal with such pulses, we call that sampling as flat top sampling. See, in your syllabus, I guess I have seen a word which is called flat top sampling. So flat top sampling is something like this. When you use it, it is a practical way of doing sampling. So when you do this, now the question is, okay, we developed all our theory and nicely shown that we can sample a signal and we can get back the original signal using impulses. But now we are saying that no, we cannot use impulses because they are practically impossible, and we are trying to use some narrow pulses in place of impulses, right? So will the previous theorem holds good? So will the sampling theorem still works when we use these narrow impulses? It's our task to show that yes, it still works. So how it works? How to show that the sampling theorem still works? So what do we mean by showing that sampling theorem still works? See, if we can show that we have taken an x of t having band limited to omega m, and if we sample that signal with p of t, and then we get the sampled signal, and then if we can get back the original signal from the sampled signal, right? If we can get back the original signal from the sampled signal, then we are sure that yes, sampling theorem works. Now let us see when we use p of t, that means narrow pulses, will we still be able to get back original x of t from the sampled version xp of t, right? Remember, xp of t is nothing but x of t multiplied with our p of t. So that means xp of j omega is x of j omega convolved with p of j omega. The answer is yes. Let us see how. Right? So how we showed our sampling theorem? We found the Fourier transform of p of j omega and convolved that with x of j omega, and showed that xp of the Fourier transform of xp of j omega has got repeated spectrum, has got x of j omega in it, and then we recovered that x of j omega with an ideal low pass filter. Now we do the same thing. So first step is compute p of j omega. So what I said previously was p of j omega, how do we compute? So p of t is periodic. So recall that now p of j omega is nothing but 2 pi into ak delta of omega minus k omega s, k equal to minus infinity to plus infinity, where omega is equal to 2 pi by ts omega s and ak are the Fourier series coefficients. It's not Fourier series coefficients, or the Fourier series coefficients of P of t. So what is P of t? P of t is this, right? Now you can solve this as a homework. For P of t, AK is equal to this. We did. Yeah, sorry. You don't need to do this even as a homework. We did last time. Not last time when we were discussing Fourier series. We found out the Fourier series for a periodic rectangular pulse. So we have taken a periodic pulse having duration minus t1 to plus t1, and it repeats every t seconds. So minus t1 to plus t1 duration rectangular pulse, and it repeats every t seconds. So this is sine k omega s t1 by pi k. So my P of j omega is nothing but summation over k, and this is 2 pi into sine of k omega s t1 divided by pi k. This pi gets cancelled, and delta of omega minus k omega s. So this we did before. This part, or you can solve this once again just as a practice for your exam, right? Okay. Now this I can further show this as this. I can write in terms of sinc function. So this is equivalent to 2 omega s t1 sinc of k omega s t1 by pi into delta of omega minus k omega s. See, this is nothing but converting this into sinc function, and you know that sinc of pi theta is equal to sine pi theta by pi theta, right? Sinc pi theta is sine pi theta by pi theta. So using this, you can show this to this. You can use this. So that meaning now P of j omega. Now P of j omega looks something like this. See, it has got a sinc function and then a series of impulses. So it has got a series of impulses at omega is equal to 0, omega equal to omega s, omega equal to minus, omega equal to 2 omega s, omega equal to 3 omega s, and so on. So minus omega s, minus 2 omega s, minus 3 omega s, and so on. But there is a sinc function. So that meaning it will have a high amplitude here So it is a downward arrow, this is an upward arrow. So this is our P of j omega. Sorry, my diagram is not so neat, but you can understand basically the point here. So P of j omega has got a series of impulses. One at 0, another is at omega s, 2 omega s, 3 omega s, and so on. But these impulses, amplitudes and polarities will be different. These impulses will have different amplitudes and different polarities. That is because they are being multiplied by this sinc function. Because they are being multiplied by the sinc function, these impulses will decrease in amplitude as we go away from the 0. These amplitudes will go on decrease as we go away from 0, and further these the signs will keep changing. So just compare this with your previous P of j omega. So now P of j omega is consisting of impulses but the amplitudes of these impulses decrease as we go away from omega is equal to 0, right? So in the previous case, when we have, when P of t is ideal impulses, we have P of j omega as something like this. So this was our P of j omega in the previous case. So previous meaning ideal case or natural case. So now what is our P of j omega? Our P of j omega now is, there is an impulse and it has got reduced its samples. So this is now meaning practical case or flat top sampling. Now you have to convolve this P of j omega with x of j omega, right? You have to convolve this P of j omega with x of j omega, and when you convolve, you apply again the same property. So now recall that xp of j omega is x of j omega convolved with P of j omega, right? When you convolve, what will you get? You will again, because x of j omega is a triangular waveform, you will again get triangular waveform. So this is at omega s, this is at 2 omega s, this is at 3 omega s, this is at 0, this is at minus omega s, and so on and so forth. So this is also omega s, 2 omega s, and so on and so forth, right? So this will be omega m. Then your second sample will be less in amplitude. So this is your omega s. This is your omega s minus omega m. This is your omega s plus omega m. Similarly, this minus omega s. So this is minus. So this is your xp of j omega. So xp of j omega will still contain your x of j omega, and your other amplitudes will be lower. This is the strongest. This is having highest amplitude, and these are having somewhat low amplitude, and that appears at 3 or 2 omega s will have somewhat more lower amplitude, right? So that meaning, but if we can recover this signal again, with an ideal low pass filter, we get back our x of j omega, right? So even if we use flat top sampling, we can still recover our original x of t, which is the continuous time signal, right? So because xp of j omega still contains x of j omega at the origin, if we can extract this portion of the signal in the frequency domain using a low pass filter, so this is h of j omega, an ideal low pass filter, we can still get back our signal. So this shows that right. We can see that xp of j omega contains x of j omega at the origin. Even when we do sampling with practical narrow pulses, instead of what? Practical narrow pulses instead of ideal impulses. By using a low pass filter, we can extract x of j omega from xp of j omega, and thus reconstruct x of t from xp of t. That's it. So the flat top sampling or the practical way of doing sampling also works. So it's not only the sampling theory not only works in theory, but it also works in practice. So we are left with aliasing. So only one more thing left is, how do we view remaining topics in this unit. If we get one class, then we will definitely finish it off. So one is reconstruction or interpolation. So reconstruction as interpolation, reconstruction of x of t as interpolation, and second concept is aliasing. So we need to cover these two things before your exam. If we cover this, then we cover the entire syllabus. So these topics we can definitely finish it off in one class. Like so, I request if there is any time for you on Saturdays, this coming Saturday. So I request you to give me one slot so that we can finish off this, and then you can go ahead with your exams. So if there is any possibility of extra class, like makeup class, I don't call it extra class because we missed a class on Tuesday. Last Tuesday, suddenly your exams got cancelled, and I was not knowing that, so I could not take the class. I was thinking that that's your exam day, and then I could not take the class. So then I came to know that your exam got postponed, and then I took the class today, right? So if there is a possibility of class, so your JNTK staff will inform me, and then we'll have a class. So and as I said, I can send you this material as a PDF. I can convert this into PDF file, and then I can send it to you over email to Asghar in JNTU Kakinada, and then he can forward to all of you.